All right, today you're going to take some notes on continental drift and seafloor spreading. Continental drift is the hypothesis that states that continents have moved slowly to their current locations over millions of years. So this first picture here, this is Pangaea. This is what we've been talking about the past week. And then it progresses to Laurasia and Gondwana. Then we have closer to our 7 continents today in their current placement. And then here is what our continents look like today. So this hypothesis says we had this giant landmass. Over time, they've slowly spread apart until we get to today. Continental drift. All the current continents were once connected as one large landmass now called Pangaea. And I feel like you've heard me say that over and over, so we probably all know what Pangaea is. The landmass broke apart and the continents drifted to their present locations. Scientific evidence for continental drift. So Alfred Wegener, the scientist we were talking about earlier in the week, he came up with these pieces of evidence. Puzzle-like fit to the continents, similar fossils have been found on different continents, and this picture kind of shows that. South America and Africa fit almost perfectly like a puzzle piece. Antarctica kind of fits up between Australia, India, and Africa. Then it has these bands of fossils. So these fossils show that if we do line these continents up like puzzle pieces, they even have these fossils in these similar band areas. So why or how can we say they weren't connected in the past if we can even see these fossil connections? Some more evidence, the remains of warm weather plants in Arctic areas and glacial deposits in tropical areas suggest that continents have moved. Another piece of evidence is that similar rock structures are found on different continents. So once again, if we push these together like puzzle pieces, these mountain areas and what makes them up are very similar to one another. So they more than likely broke apart in this area. At first, despite the physical evidence, continental drift was not accepted because no one could explain how or why the continents have moved. How did they move? Scientists still lacked a theory for why and how the continents were moving. Without evidence for a mechanism, you might think it happened like this. But that was probably not the way it happened. So Let's look at how it did happen. Using sound waves, scientists discovered a system of underwater mountain ranges called the mid-ocean ridges in many oceans.
During World War II, scientists at sea were using sophisticated echo technology to track submarines when they turned up surprising information about the ocean floor. There they found a stretch of underwater ridges made of continually erupting volcanoes.
The mid-ocean ridges formed when molten rock rises from inside the Earth and then pushes the crust apart.
A vast spreading seafloor strong enough to move the continents. Not only is new crust formed at mid-ocean ridges, but it dips back down again into the interior of the Earth.
You put this all together, and what you get is plate tectonics. The idea that the Earth's crust can be broken up into large pieces or plates that consist of both continents and also pieces of oceanic crust moving together over the face of the Earth.
When two plates collide, sometimes one is pushed downward and melts into magma. Eventually, this red-hot material rises to the surface and explodes, creating a volcano. So new crust is born at mid-ocean ridges and destroyed at deep ocean trenches, like a never-ending conveyor belt. And two plates simply nudging each other can cause catastrophic results, like when the San Andreas Fault slipped in 1906. How fast do the plates move? If you live in the US, you're probably standing on the North American plate. In the course of 1 year, the ground under your feet will move about 2 inches. And over long periods of time, that's enough to reshape the Earth, build mountains, trigger earthquakes, and create volcanoes.
All right. So, in the 1960s, Harry Hess suggested the theory of seafloor spreading to explain the ridges. So he said, all right, I kind of believe this Wegener guy, but why? Well, let me tell you, this is why, or how. Hot, molten, melted rock is less dense than the Earth's crust, so it rises upward to the surface at the mid-ocean ridges. Then it pushes the crust up and sideways, carrying the seafloor away from the ridge. So that's what this picture is showing right here. It comes up, cools off, goes sideways. As the seafloor spreads apart, the process repeats. It's just kind of like a conveyor belt. It's continuous. The magma moves up to the surface, flows from the crack, cools, forms new seafloor. Seafloor spreading. So what is some evidence that says, okay, we think this is how it happens, the how, but how do we know that's true? Well, Harry Hess said, well, this is some evidence. Youngest rocks are located closest to the mid-ocean ridge. So when that magma comes up, cools and hardens, that makes new rock, so that rock's younger. And then also they can look in the rock and see reversals of Earth's magnetic field are recorded. And so they can see the change in the polarity of these types of rocks, so that gives them more evidence. So in summary, here we go.
Enjoy this movie, then visit brainpop.com for much more. Are you sure this thing is rated for this depth? You bought it from an Air Mall catalog. Oh, great. Dear Tim and Moby, when I look at a map, it seems like some continents fit together perfectly. Are my eyes playing tricks on me? From Georgia. You're not seeing things, Georgia. Some continents look exactly like puzzle pieces that snap together. Early map makers suspected that they were once all connected. In the early 20th century, a scientist named Alfred Wegener called this supercontinent Pangaea. He thought different chunks of it broke off and slowly moved apart. Over millions of years, they formed the continents we know today. Wegener couldn't explain why Pangea split up or how. But there was some evidence to support his idea. Fossils from similar plants and animals had been found oceans apart. The age and type of rock layers matched up too. Wegener's theory of continental drift provided an explanation, but his ideas weren't taken seriously until long after he died. In the 1950s, scientists began mapping the Mid-Atlantic Ridge. It's a mountain range running 10,000 miles along the ocean floor. Tests revealed that the farther you got from the ridge, the older the seafloor was. So a geologist named Harry Hess proposed a revolutionary idea. New seafloor was forming at the ridge and spreading outward to make room for more. In other words, the surface of the planet was moving. Hess called this process seafloor spreading. It seemed to indicate that rock was being forced up from inside the planet. Nowadays, we can see this rock formation in action. Wegener had guessed something like this, but he had no way to prove it at the time. As he suspected, there's a lot going on beneath the Earth's surface. Up here, everything seems pretty cool and stable. But miles below our feet, it's a raging inferno. The deeper you go, the hotter it gets. Earth's center, or core, is as scorching as the surface of the sun. All that energy wants to escape like steam inside a boiling kettle. It pushes outward, putting immense pressure on the middle section, the mantle. Standing in its way is the lithosphere, a rigid layer of solid rock. Well, the lithosphere isn't like a smooth shell. It's cracked into pieces, each one a different shape, size, and thickness. We call those pieces plates. Yep, the Mid-Atlantic Ridge is the border between several plates. They're being dragged apart by forces from deep inside the planet. You can think of it like a pot of soup. The Earth's core is the burner, and the mantle is the boiling soup. As the soup near the burner heats up, it becomes less dense and rises. When it gets to the top, it cools off and sinks down toward the heat. In physics, those are called convection currents. A similar process is driving the mantle, and it's taking the plates along for the ride. That movement is called plate tectonics. It's the engine driving the constant transformation of our planet's surface. Plates have been bouncing off each other for eons. The oceans have expanded and contracted. Land masses have smashed into each other and broken apart. The plates move about as fast as your fingernails grow, so we don't see the ground sliding around under our feet, but we do sometimes feel it. Yep, I'm talking about earthquakes. Seismic activity is greatest along plate borders. At convergent boundaries where two plates collide, at divergent boundaries where they pull apart, and at transform boundaries where they slide past each other. At all three boundaries, there's enormous pressure on the Earth's crust. That's the topmost layer of the lithosphere. The pressure can build up for years. The longer it takes to release, the bigger the earthquake. Yep, and plate movement drives volcanic activity too. At divergent boundaries like the Mid-Atlantic Ridge, there's a gap in the lithosphere. So magma, molten rock from the mantle, is constantly pushing up along the boundaries. These are the most volcanically active places on Earth. Volcanoes are also common at boundaries called subduction zones. That's when a dense ocean plate converges with a lighter continental plate. The heavier plate gets pushed below, down into the mantle. Some of it melts, and the magma erupts farther inland. The Ring of Fire is a massive chain of these volcanoes. Dense sedimentary rock making up the Pacific seafloor is subducted, transformed into metamorphic rock through pressure and heat, and then recycled as igneous rock through volcanic eruptions. In other words, plate tectonics drives the rock cycle, the constant process of transformation and renewal of the Earth's crust. It also creates our most prominent geologic features, mountain ranges. That happens when two continental plates converge. Since they're both about the same density, neither one subducts. Instead, it's like a slow-motion car crash. The plates buckle and warp. The land pushes up into jagged peaks. The Himalayas are still growing from a plate collision that began 500 million years ago. Yeah, Alfred Wegener's theory has come a long way in 100 years. He was practically laughed out of the scientific community for his ideas. But today, plate tectonics is the unifying theory that ties together the entire field of geology. What do you mean, out of juice? We're stuck here? Now what? Oh, thank you. Visit us at brainpop.com for more on this topic and